so let's get started. Divergence, curl, and del. We'll talk about them in 2D, and then we'll talk about them in 3D. You saw the videos for today. There's only a few things I want to mention. We're going to start with divergence. All right, we've heard the term divergence before. This is a little bit different than the divergence we talked about in Calc 2 when we were looking at divergence of a sequence or series. In vector calculus, it's specifically used to measure any given point in a vector field's magnitude and whether it's a source or a sink. All right, we'll talk about what those mean here shortly. Basically, it represents the volume density of the outward flux of a vector field at any given point. So basically, to start to get an idea of this, imagine as air is heated, it expands in all directions. Okay, so that source of the heat would be a source because it's pushing everything away. So the velocity field would point outwards. So this is what we would call a source. The sink is the exact opposite of that. Gravity is a sink because it's an attractive force. Our vector field would all be pointing inwards towards that point. Okay. Now, what we find at any given point in most vector fields, there's going to be some things that are going away from it and some things are going towards it. And so we kind of look at the tendency to be a source or a sink. You know, it's not an absolute. It's not like gravity where it's all going towards the point, or, you know, it's all going away from the point. It could be, but it could be just some is going towards it and some is going away, or vice versa. So think of it as like a measurement of outgoingness. The nice thing about divergence is, you know, we'll do it at a point today, but later this semester, we'll be able to use divergence to measure flux, or the amount of something going out or in on an entire surface using an integral, because an integral will add up all the points. What's that? Yep, we'll get our flux integrals in. So the expansion of a fluid with a velocity field F is captured by the divergence of F. One thing I want to mention, divergence is a scalar. It is just a positive or negative number. Positive means it's acting as a source. Negative means it's acting as a sink. So here are like some really obvious examples, right? We can see that the origin is acting as a source. Excuse me. Thank you. In these two examples here, we can see the origin is acting as a sink. So again, what divergence does is it basically measures the outgoingness or attractiveness at any single point. Not that any point is necessarily all repelling or all attracting, but it measures, is it more attracting or more repelling at any given point. All right, well, how do we calculate it? This is the easy part. It comes from the partials, because think about what we're doing. We're looking at the way something is changing, the way something is going towards it or away from it. So what we want to look at are the partials. Are they positive or are they negative? And we sum them together to get the total amount of divergence. So a 2D vector field, we sum up the partials. And notice there's nothing crazy going on here, right? It's the partial of the first component with respect to X plus the partial of the second component with respect to Y. The 3D flux, we add on a third component. Now I'm pointing this out because you'll see when we look at curl, they actually flipped. So calculating divergence it's like the gradient almost. It's about as easy as anything we're going to do, because we're very good at partials now. All we're doing is summing up the partials of each component And just remember that each component is lined up with your first component X, second component Y, third component Z. Now, obviously, you do not have to memorize this formula. You have the note card for the exams, or you can use a note card for working on the homework. We just need to know how to use it and have an idea of what it's telling us. All right. One of the things I'll mention, and I have links, and they weren't linked up to the calendar, so I put them into the calendar too. There's a website I like called Better Explained that gives some intuitive explanations to some of the concepts in math. And so I linked its intuitive explanation for divergence and curl. So, if after our talk today, you're still like, I'm not quite sure what I'm looking at with divergence or with curl, go check out one of those links, see what you think. I think they do a good job of kind of giving some real world examples. Okay, let's talk about the curl. So the curl calculates the amount of rotation of a vector field at any given point. So it's similar to divergence in that it calculates an attribute of a vector field at a single point, but the attribute it's looking at is different. Okay, now we're looking at its tendency to rotate at any given point. And what we can do is we can add up the curl at all the points to get the circulation of the vector field. So the curl is actually a vector that gives what we call the circulation density, or the rate of circulation. Again, you add that up, you get the total circulation because we're accumulating rate. So if you imagine taking a whirlpool and then you shrink it down smaller and smaller while keeping the force the same, there's going to be a large amount of power all of a sudden in a small area, so we would get a large curl. The faster that rotation is. The slower the rotation, the smaller the curl. So again, it's a measurement of rotation. We can have a zero curl, which we're also going to talk about here in a little bit, because that makes something very interesting for us too. I want to give you kind of an idea of what this curl is. So the curl is the amount of twisting going on when the path is shrunk down to a single point. So, imagine putting like a flat surface in water, like that site Better Explained talks about using an oar, right? And imagine putting an oar down in the water. Okay, what happens with the oar? Does it go forward? Does it go back? Or do you feel it twist? If you feel it twist, that would be the curl. That would be a circulation density, because what's happening is one side's getting pushed harder than the other. It's not in equilibrium. When it's in equilibrium, we have a zero curl. The harder twist, the larger the curl. No twist, we got a zero curl. Now this is going to be something that's going to be really interesting for us as we go on, because we're going to start to talk about conservative and non-conservative vector fields. When the curl is zero, think of curl being zero as things being in equilibrium. We have what's called a conservative vector field, which means it's path independent. In other words, no matter what path we take between 2 points through the vector field, the amount of work done by the vector field is going to be the same. Well, now we already have a way of identifying it. If we get a zero curl, and it has to be zero for all the points, we get a conservative vector field, which means it's path independent. We're going to rehash all these terms again next week. So I don't want you to worry that I'm throwing too much at you at once. It's going to come back again. Okay. Now, let's assume that we have a gradient field. All right. We looked at this. We talked about this last time. A gradient field is a vector field, but not all vector fields are gradient fields. We have a gradient field if there is a potential function whose gradient made our vector field, right? So if we know something's a gradient field, then we know it's made up of the partials of some function. Then we can calculate the curl df2 dx. So this is the one where I said it's opposite, right? df2 dx minus df1 dy. 1 dy. That's our 2D curl. And we'll talk more again about gradient fields and potential functions next week as well, because again, there's a lot of really cool properties when we know something is a gradient field that don't exist for all vector fields. But if this curl comes out to be 0, the one thing we do know is we have a conservative vector field. Now, think about what happens if we have a gradient field. So this would be the partial with respect to x. This would be the partial with respect to y. We'll talk about more about this next week, so I don't want to actually do it on here. This would be the partial with respect to x. This would be the partial with respect to y. That means we would do the partial with respect to y, then the partial with respect to x. So this basically would be f sub yx. This here would be f sub xy. What do we know about f sub yx and f sub xy? If we did everything right, they should be the same, which means we'd get a curl of 0. So all gradient fields are conservative. I kind of, that was something we're going to get into next week more explicitly. So I gave away the punchline, but we're talking about it now. So might as well. But we'll look at that more next week. Today, we're specifically going to look at calculating divergence and curl, and using the curl to identify if we have a conservative or non-conservative vector. The curl in 3D, this looks kind of familiar, right? This looks a lot like cross product. Very similar, it's same idea as cross product. So the curl in 3D of a vector field could be done as a determinant of a 3x3 matrix, or you can just use this formula here. That's totally fine. You're going to have your note cards. You can use Wolfram Alpha and say, find the curl of this vector field. That's fine too. One of the things I want to point out here, notice the curl actually comes out to be a vector, right? In 3D. So that means it has magnitude and direction. So the magnitude is basically the speed of rotation. Nothing crazy going on there. But that means it also has direction. The direction, remember the or example that we were talking about? The direction would be the stem of the or. Okay, so it's the axis of rotation. So let me do this so it's on camera. So if the direction if the curl goes in the direction of my fingers, the direction the vector is pointing is upwards in the direction of my thumb. If it was curling this way, downwards. And as you can imagine, because we're in 3D, we could have a curl that goes like this, right? Any possible direction. And what the vector direction gives us would be that piece of the or that we're holding. It's not going to be a big deal for us because we don't really use that direction very much, but I just want it is a vector value quantity, so we should talk about it. With the 2D curl, because we're in 2D, we just get a positive or negative. And that just tells us which way it's spinning, clockwise or counterclockwise, because it's either coming out of the board or into the board. Okay. Last thing I want to talk about, and then we're going to look at one thing in CalcPlot 3D, and then I'll let you guys go. The del operator, only because it comes up. This is a symbol on there. That square, the rectangle here should be multiplied. The del operator, remember we saw this in gradient. The del is just telling us to take the partials. So basically, this is supposed to be dot product. So let me write it up here, what it's supposed to say. So when we're looking at divergence of f That's the del dotted with the vector field F, which means I'm just going to do the 2D. The 3D is just one more component. D dy is being dotted with F1, F2. Okay, so we're doing dot product. So that means df1 dx plus df2 dy. So that's all that's saying. There's nothing crazy going on with the del operator. It's just something we've seen it before with gradient, right? We write, now this was dot product, so that dot is in there for a specific reason, but when we do a gradient of some function, think about what we do, right? We do df dx, df dy, df dz. So that's what this triangle, upside down triangle, it's called del. That's the way it's working in these. Same idea. So that's what del is. It's not a major concept. It's just an operator telling us to take the partials of the function or the vector of the vector field. Okay, let's do one thing that I think is kind of cool, and then we'll go over to the worksheet. So let's, this is something you guys can play around with, but calcplot 3D. Bring up a vector field. I'm just going to use the one they have in there. It's only a 2D vector field, so let's just restrict it to 2D. Okay, now we saw we could do flow line solution curve. We can also do curl at a point. So let's drop a point in there. That's the curl. That's what's making it rotate. Now watch what happens as we move this point around. Notice how, oh, gee, where the vectors are longer and in the same direction, it starts rotating faster. Oops. Right? We can find different spots, and at any of these spots, we can calculate the curl because we know how to do that, right? It's that df2 minus dx minus df1 dy. So at any given point, we have a curl. Look, there's the curl going in the opposite direction. So that's telling us the curl is negative in this case, because right now we're only looking at a 2D curl. So this is something that we can, that you guys can play around with for the vector field you're looking at. Now I just did the default one on here, but we can actually calculate the curl for this. So our curl, again, we're just doing 2D right now, is df2 dx minus df1 dy, which for our vector field, if you can't see it, it's m and n. M is f1, n is f2. So df2 dx, so I'm taking the derivative of n with respect to x, which would just be 1, and then df1 dy. So the derivative of this guy with respect to y, well, x with respect to y is 0, and negative xy with respect to y is negative x. So 1 minus negative x or 1 plus x. That will give us the curl at any point. And it makes sense that it varies because we saw that the rotation was different depending on where we were in the vector field. If the rotation had been constant, we would have expected this to be constant. If the vector, if it would have been 0, we'd expected it to be 0. In fact, here's a vector field. We looked at this one last time, yx. If we calculate its curl, well, df2 dx is going to be 1 minus df1 dy, which is 1. This has a curl of 0 everywhere. That's its general curl. All right, well, let's see. So we're going to put in y, x, Now, when I move that point around, no matter where I have it, there's no rotation. That's what you should see in a conservative vector field or a path independent vector field. That's what it looks like when our curl is 0. All right, so that's something, this is something you guys have access to that you can play around with when you're working on a vector field. It'll work for 3D vector fields too. Oops, I got to get this out of 3D. Okay, so you can see here, it even puts in the vector for us now because we're in 3D. That's that axis of rotation we were talking about. And you can move that point around. And we can see, depending on where the point is, we have a different rotation. In all of these, that's rotating the same way. Let's see, which is why that purple vector is always pointing in the same direction. And we can see it is in fact a 3D vector field. The other thing, again, this is something you guys can play with. You can play with it as you work on the worksheet, or you can play with it on the homework, just to kind of start to get a visual of what the heck is going on with this curl and divergence. We can do divergence at a point. Remember, it's the amount going in or to a point. So the point is that let's start off in just 2D here. Let's take that out of here for right now. Okay, so here's our divergence. And now the way this works is, we've got the circle. This point here is the point where we're measuring the divergence. The circle is kind of saying, okay, well, what's going in towards the point and what's going out towards the point? So these ones that lie inside the circle are sinks. They're being attracted towards the point. These ones that are starting outside the circle and being repelled away, those are representing a source at the point. So let's go to a very nice, easy point. Let's just do 1, 1. Okay. All right, so we see something like this, and we want to know, okay, well, geez, is that a source or a sink, or is it neutral there? Remember, we can calculate this. So now I'm doing it for this vector field here. I need to go back to the original. So the divergence, the divergence of F, it just comes from adding up the partials. Well, the derivative of y with respect to x, oops, sorry, it's a scalar, is 0. Actually, let's write the whole thing. Derivative with respect to x of y plus the derivative with respect to y of x is 0. So that tells us that at any point in this gradient field, these things are in balance. There is as much going in as there is coming out for this particular gradient field. Okay. And what we would do is we look at 2 things. We look at how many of them are going into the circle, but also the magnitude of them going into the circle. And you can see right here at the bottom, it's calculating the divergence for us. I think it does that for the curl too. We'll go back and double check. See how it's 0 everywhere? Well, it makes sense based off of our divergence. I don't know if it calculates curl as well. Let's see. Yeah, it doesn't look like it calculates curl for us, but it calculates divergence, probably because it's such an easy calculation. Okay. So just to wrap up, here's the big things I want to take away from today, right? Curl is basically a rate of rotation. Like how quickly is this thing rotating at a single point? Divergence is the tendency to act as a source or sink at a single point. We need to be able to calculate them in 2D and 3D. We have formulas for that. And then the last thing is that if we have a curl of 0, we know we have a conservative vector field and it's path independent. If the curl is not 0, then we know that it is non-conservative, which would make it path dependent. Those are the biggest takeaways from today, just those bullet points. If we can take that away from today, then I think today's a huge success because we'll be able to leverage this stuff later. So what we'll do on Tuesday is we'll get introduced to line integrals. So we actually won't look at this then, but we're going to see as we start to look at ways of calculating line integrals, how this stuff plays it.